And with this, we reach 5 minutes past 9. So we have a first talk about design implementation of high-speed data link receiver using GNU Radio. And the floor is yours for half an hour.
Okay, thank you. And hello, I'm Ceren. And I work as telecommunication design engineer at Planes. And today I will talk about our high-speed receiver and details about it. So first I will briefly explain what we do, how we do it, and our satellite communication links. Then I will go towards the more detailed one, from generalized links to high-speed link to high-speed downlink, and my receiver algorithm and sub-blocks of it, and so on. So for starters, Planes Satellite and Space is a Turkish company. We have built 3 years ago. We were founded 3 years ago, and within 3 years we have successfully sent 9 satellites to LEO orbit. 5 of them were actually test satellites, and we sent them just to flex on our capabilities, learn how to do satellites. The ones at the bottom are our test satellites, and the ones that on the upper corner are the 4 IoT satellites. Gizem will talk more about what we do with those IoT satellites. We are sending our satellites using SpaceX Falcon 9 missions, Falcon 9 rockets. And we have 3 ground stations that we have built ourselves, 2 of which are situated in Ankara, Middle Anatolia, and 1 of them is situated in Erzurum. This is actually a picture of our ground station in our headquarters. All of our ground stations are GNU Radio based, and we use USRPs with that. Also, we have various agreements with different ground station service providers, and they are GNU Radio based as well. So I work extensively with GNU Radio. We do also have SatNOX stations. We cooperate with them, so you can use our SatNOX stations to get a plan for a listening session for whatever satellite that you are interested in. I have a video here. It summarizes what we have done so far quite well. So I would like to play that. This one. For next up, we have, as you have seen in the video, we have IoT satellite. So I will give you a brief explanation of how we start communicating with the satellite. I couldn't, yes. First off, okay, once the integration is done, we send our satellite to Germany, actually. We work with ExoLaunch, and they perform integration with the deployment pod. So they sent that satellite after integration, they send it to SpaceX to America, and after that we wait for the launch date. And during launch date, we do the following. We first wait in our mission control room and to hear separation confirmed. And usually, well, luckily, our most recent travels were done around Turkey, on top of Turkey. So we have satellite comes to us very soon after the separation is confirmed. I have another video for that. Yes.
3, 2, 1, ignition. And liftoff Falcon 9, go Transporter 11. Connecta IoT 1 deploy confirmed. Connecta IoT 4 deploy confirmed. Connecta IoT 2 deploy confirmed. Connecta IoT 3 deploy confirmed.
Once the deployment is confirmed, as you can see here, this was actually the live, this snippet is actually taken from live recording, live broadcast on YouTube. We were here, and once the separation is confirmed, we wait for satellite to come exactly what elevation we need, and then we attempt to communicate with it. So, why is it very important to communicate with the satellite is because first, if you can establish a successful communication, it means that it's alive, it's working properly. Second, we want to get vital information as soon as possible so that we can intervene with it as soon as possible. And also, if you establish a communication, it means that you have found your satellite. This is actually, it's been going quite well. We have established communication just 7 minutes after connected T2.1 separation and 3 minutes after T.1 and T.3 separation. On the right side, you can see us in the ground station right after T.1 successful communication. Also, you can watch this live video over the internet. I added the link to watch it. It's entirely in Turkish. However, you can see how we react here once the separation is confirmed, how we are working together with, you see the GNU Radio flows here, and it's very exciting in general. So speaking of which, about the spectrums, we pre-plan some SatNOX stations and we tune them for our satellite. I've added the link for Connecta IoT1 observations. You can just write Connecta and all of our satellites will show on the SatNOX. And you can actually see the waterfall of it. There's actually an audio file. Well, it's not actually audio, but if you want to listen, the spectrum, you can as well. And also here says data section. And in that data section, SatNOX ground stations use GNU Radio as well. And they decode our actual telemetry data and show you in a screen like this what's written in there. So we usually put vital information about the satellite there, but we sometimes put fun things to write. For example, this is from 29th October. It was the birthday of Turkish Republic. So it says, Cumhuriyetimiz 100 yaşında. It literally says our republic is 100 years old. Speaking of which, in Turkey, we have 25 satellites, operational and functional satellites right now, 9 of which that plan has sent. So this is very few. It's not bad, but it's few. What we want to do is we want to increase it. How do we increase it? We want universities to send more CubeSats. We want private ventures to send more CubeSats. And we want everyone actually to contribute to the space science. That's why it's important to have such organizations, especially open source environment organizations. Let me talk a little bit about our communication links. We have 6 links in total. UHF link is the main lifeline of a satellite. You send commands there, you get vital information from there. High-speed link is, well, it's vital too. You can send software updates and you can download images, videos, huge chunks of IoT data. We've actually tested our RF, it's not optical ISL, it's RF ISL link to transfer IoT data from one satellite to another so that, let's say, the first satellite A has a data that I'm interested in, but it's not in my line of sight. So what I do is I schedule a command, it sends to another satellite, but and the second satellite is in my line of sight, so it sends to me back. We have direct-to-satellite link and gateway-to-satellite link. These are all IoT links, and Gizem will be talking about them. And next, we have an X-band downlink, which is still in progress, still in being development, and we will be using it for Earth observation purposes. So in order to hype you up about communication links, these are the examples of what we have done using our high-speed link so far. Those 3 images are taken with a camera, downloaded with our high-speed downlink. These 2 videos, actually this one is very nice. Since they were test satellites, we did... Okay, that's...
Freundschaft ist eine lange Reise. Es gibt süße Zeiten und Zeiten, in denen es rund läuft. Wir sind da...
Okay, German advertisement. Since we have sent so many test satellites, we did kind of crazy stuff with them. Actually, Connected T1.2 has a selfie stick, so you will see the video of it. As you can see, it's very spooky, like there's no one there. Is there anyone there? It always amazes me, space. And now we have another 4K video shot from space. Do we have any? Yeah, no. Actually, I need to adjust this. Yeah. Okay. Why is this not playing? This shows Mediterranean Sea and Black Sea. I don't know why this is lagging, but the original video isn't. It shouldn't be. You can see the sun here. I think that's Cyprus. Is it? Yeah. There are way more videos in our YouTube channel. You can check them if you'd like. So let's get started. So how did we download all of the information that all of the videos that I've sent? We are operating in full duplex. We are operating at S-band, which is between 2 and 2.5 gigahertz. Our payload, which is the thing that you put into your satellite to communicate with the ground station, is our own design. And in the ground station, we have GNU Radio plus SDR. For waveform, we always use international standards to be able to work with different international organizations, and the most prominent one is CCSDS, as you know, and its features are as follows. We do have a scrambler, we do have concatenated convolutional code, which is Reed Solomon plus convolutional code with different puncturing rates, and we do have a QPSK modulation. So in the link, I have actually made a MATLAB simulation using ground station properties, antenna properties, RF properties of the transceiver payload, and our actual satellite TLE data. And turns out that our dynamic range is in between minus 101 dBm and minus 83 dBm. As you can see here in the... Is this working? Yes, this is working. Here you see the Doppler, expected Doppler shift curves in here. It's different for the dashed line is for uplink, the other line is for downlink. So as you can see, maximum Doppler shift that I will be getting is between plus and minus 50 kilohertz. Moreover, we can define Doppler rate as the rate of change is the change in unit time in Doppler frequency. So as we approach to 90 degrees, so the satellite is passing from your top, Doppler rate increases because the speed, the frequency changes very rapidly. So we have maximum of 777 hertz per second of Doppler rate, which our receiver should be able to recover from. Also for data rates, it ranges from 125 kilobaud to 4 megabaud. As I said, it's high-speed link, but I've put some very low speed, like 125K, just in case, so that if everything fails, maybe something happens with this antenna, some operational problems happen, so that we can still communicate with it. Also, we will be doing continuous transmission, so that when the satellite is sending data, it just sends data, and when it's not, it just keeps sending idle gibberish frames. So here is my design. As you can see, there are lots of different blocks here. The white and black ones are generic GNU Radio blocks like USRP source, automatic gain controller, and so on. The red ones are my additions or my modifications. These phase stepper and node synchronizer, they are borrowed from SatLab's GNU Radio OT module. And in the bottom, you see a container. It actually shows up like this in the GNU Radio flow graphs, so that when operation team uses it, when test team uses it, it looks nice and easy to navigate around. I will go down one by one and explain you main reasons why we did it, what we did. So first off, we're working with QPSK modulation. And the biggest problem is, well, one of the biggest problems is phase ambiguity. Here you can see my symbols there in 4 quadrants, but my receiver, my symbol synchronizer, here, Gardner symbol sync, cannot possibly know where my first set of symbols start, at which phase my symbols will start. So it can, if you imagine, it can be started at 45 degrees and it looks like this. It can be starting at 135 degrees, so it will be shifted 90 degrees. It can start the other one, another shift, other one, another shift. So I have 4 different probabilities for where my symbols should be located at. In order to combat that, we can use differential encoder, which is NRZM encoding. And what that does is that instead of modulating bits, it modulates, well, it first maps bits into bit transitions. So therefore, you get a 180-degree symmetry over the y-axis, no, x-axis. That's okay, but we still have 90 degrees of phase ambiguity. So they would be looking like this or just 90-degree shifted version of it. In order to check for it, receiver should be multiplying it by 1, like at the 0-degree phase, and with 1J at 90-degree phase, and check which one is correct. How do we check it? We check it by syncing to our header. At the output of the frame, sync here. I've got some possible solutions for it, like it's straightforward, right? Logic says it multiply it with 1, check one branch, multiply it 1J, check the other branch. However, this does not work in GNU Radio 3.0. I'm assuming because of the buffering system, first branch and the second branch, they are operating at different data rates in practice. For example, if I have a sync here, inputs are consumed and outputs are generated here, but then nothing happens here, and vice versa. So therefore, buffer here cannot know how many outputs to consume, how many outputs to push to either of the branches. Therefore, we lose frame count. Another possible solution is that I've attacked the buffer directly. So, okay, buffering doesn't work, so I will open up a FIFO. 2 separate FIFOs, and I have 2 separate flows in the below. So here, I generate my samples. This goes to here and here. They are duplicated. They are sent in a buffer and 2 separate buffers. And 2 of these flows are actually working separate from each other, independent from each other. Although this solution works perfectly, I have no frame counts, I have no sensitivity losses, so on. However, this is not a good solution. Because imagine if you remember the ground station that I've showed you, if I put 3 different flows to 9 satellites for just only 1 link, well, it's not a good system. So what I did is I opted out for a SatLab solution, and here, yes, here, as you can see, it multiplies phase stepper, does the multiplication of phase shift, and it's directly linked to my frame synchronizer. So if the phase is okay, if there's a synchronization, it says, okay, phase, you found the correct phase. If not, however, our samples kind of start to pile up. I'm not sure if that's the correct word to describe it, but we need some sort of corrector block to ensure every sample is being treated by every one of these blocks. So what it does is that if there's a sync, nothing. If there is no synchronization, it just slows down the production of samples at the output. Also, with that we can resolve phase ambiguity problem. Now I will move on to Doppler compensation here. So in order to avoid some costs, actually both at the uplink and downlink, we do Doppler compensation using this piece of code. It's actually developed in Python. What it does is that it makes use of this satellite tracker library, and it reads TLE data. TLE data is like two-line element data, and it kind of computes radial velocity. So using that radial velocity, you can easily calculate the Doppler shift that your satellite is under to, that your satellite is subjected to. So I calculated here, and I probed those values, and I just put it to my channelizer FIR filter just to correct for it. That's tackled too. Another issue we have is that, well, the symbol synchronizer block is specifically geared for high speed. What it means that it requires lots of samples to correctly operate. However, when I go for like 125 kilowatts, well, it does start working a little slow. So what I did is basically I made the resampling ratio a managed parameter. So if it's less than certain, if the baud rate is less than some certain point, output sample rate is increased. Another problem that we like to tackle here is that, as I said, my communication channel is a continuous channel. So USRP source is always getting some frames. I'm getting always some output here. So if I keep counting my idles, or if I push those idles to mission control software, everything fails. So what we did is, we're actually making use of space data link protocol in the upper layer, and we divided idle channels we've assigned idle channels to a particular virtual channel, and data frames to another virtual channel. So I get rid of them by checking the virtual channel. Also, it's a simple block, it's a PDU counter. The more PDUs come in, it just increments it. However, it will be relevant later. So here is my test schematic. I have one RF shield box here. This line you're seeing is RF line. Those below, those downward arrows are my control lines. So in RF line, I have my transmitter. It outputs 33 dBm, quite high. I have various attenuations, and I have a variable attenuation, and I have measurement here. So I control this variable attenuation to see at which point I will get 1% of packet error rate. I also control USRP using GNU Radio and my computer. I also control the transmitter like that as well. And the computer I've used is a pretty standard laptop that we have. And on the left here are the results. So for 4 mega baud rate, I have achieved minus 101 dBm of sensitivity level. And if you calculate the what is supposed to be using minus 174 plus 10 log baud rate plus noise figure plus implementation loss and minimum SNR, it's actually pretty close to the theoretical value. On the right side, you have see the end result of all of these work. It's actually taken a few days ago. It's a real satellite pass. It's one of our Connecta IoT 1 satellites, Connecta IoT satellites. You can see the signal coming in here. We have some different probes for operational purposes. You can see the elevation degree here. It's at well, 30-something degrees. You can see the constellation here. It's pretty nice, actually. And I have my counter here. So, about high sample rates. Well, as I said, I've even added a simple PDU counter because if you're using Python, well, high speeds won't gonna happen. It's just working way too slowly. Actually, for this setup, I used to have a PDU counter in Python, and it was giving me overruns. So when I changed it, it worked perfectly fine. Also, I've spent quite a lot of time. I have wasted quite a lot of time using SDRs connected with USBs. They claim to be able to reach that amount of sampling rate. However, USB 3.0, it's just like a natural bottleneck because like there are lots of USB ports on your computer, so they are sharing that resource. Also, your design, of course, should be compact and blah, blah. And another important point is that there is a debug file. There is actually a configuration file of GNU Radio, and here says the debug level. It's by default debug. It should be emergency, because when it's debug, it produces random informational output, and it prints out to your console. It says, for example, CRC, okay, CRC, okay, CRC, okay, CRC, okay. I have 1,000 frames per second, so it slows down. If everything fails, just use no GUI. And in conclusion, yes, we have talked about them. Tests verified that the receiver works at 4 megabaud. I have also didn't include it. However, I have tested for TLE error as well. So here we have this Doppler graph, Doppler frequency graph. I calculate my Doppler frequency using TLE data. But what happens if my TLE data is wrong? Especially during commissioning phase, it's usually wrong. What happens is that my Doppler curve changes a little bit around this center point, but the Doppler rate changes a lot more. So I have both a Doppler rate error and shift error, and I've used GNU Radio to simulate for that. I didn't include the outputs, but well, it was able to work with 10 kilometers, plus minus 10 kilometers TLE error, which is quite high. We never get that. This design works on different laptops. It works on ground stations. It works perfectly. So I would like to talk more about how I use GNU Radio in satellite communication, because I use it daily. I use it extensively. I use it for payload mockup, for instance, for starters. We were actually buying, that's funny, we wanted to buy a professional grade modem, and they had the receiver and transmitter structured in 2 very different waveforms. I asked them, okay, can we make it symmetric? Like, can I just use my receiver as a transmitter? And they looked at me dead in the eye. The reason why I want to mock up my payload is that I want to recreate my payload is that we're a small company and we are working very fast. Normally it takes years and years and years to build a satellite, to build a payload and send it to space and blah, blah, blah. But we're doing it in the order of few months. So I do support developers in that sense. SDR is a verified equipment. GNU Radio, I know it works perfectly well. For example, I measure QPSK output EVM of my waveform, and I go to the digital designer and say, oh, your EVM is, worse like 3%. So we use for that. Also, we use it for bit level operations and check if they are sending me more bits, because they always do, and it causes some problems in forward error correction. I use it for channel modeling. As I said, I have kind of simulated. You know how expensive Doppler simulators are? Well, it shouldn't be, because we can use STR. As I said, I simulated Doppler error. I can simulate real Doppler case. I can simulate my amplitude variation. And I also even simulate. Leo is a very crowded place, so we have lots of interferences. I actually mock them as well and see how my receiver reacts to it. Another great thing about GNU Radio is that when things go wrong, in emergency cases, I just close the GUI, open the flow, change something, move on. So in a satellite pass, you usually have around 7 minutes, 10 minutes. So if I used something like professional grade modem, something like that, it wouldn't be the case. I wouldn't be able to recover from an error. I have put some thoughts in here. Well, pros of using GNU Radio is obvious. It's fast. You can use it for fast prototyping, testing, and it's ready to use. You can just give it them to people. It's cheaper. Design is flexible. So when you buy a professional grade modem, your design kind of gets fixed. However, in Plan S, we would like to do interesting things, so we sometimes change our waveform. It's open source, so everyone's creativity gets to be involved in my design, like, where's he, Danny Lestevas? Hi. And let's talk about the bad things. Well, the actually huge problem I have here is in the last. There is no inherent mechanism to perform a version check. For example, when I open my flow graph and I accidentally disable a block, I wouldn't know unless it gives me an error. Sometimes, well, more often than not, it doesn't produce an error. I just disable something important. I change something important by accident. And there is no inherent mechanism to do the version check. And believe me, I've tried everything. I've tried naming it. I've tried comparing Python files. And when you consider 3 ground stations, lots of test laptops, personal laptops, different teams, operation team, test team, integration team, telecom team, blah, 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 it's just a mess to do the version check. Also, related to that, cross-platform compatibility is a huge issue. Someone is using Debian something blah, something dot blah, blah, and someone else is using Linux 22, someone else is using 24. We actually froze some disk images. We have some disk images that is like, we found an optimal version of Python, UHD, GNU Radio, Linux, and so on, and we took the disk image of it, but that's not a good solution as well. And also, when I develop some OOT modules, like, I have to rebuild it every time I make a tiny little change, and I do lots of changes. So thank you for listening, and I would like to say it was a great journey to be here. Let's keep in touch. If you have any further inquiries, whenever you want to ask something, you can freely send me an email. Thanks. Bye.
Thanks. Okay. I believe we have a few minutes for questions. Is there any comment or questions from the audience to the speaker?
I'm sorry, I forgot that.
I'm really curious about your resampler plug. So, do you need to do like small resampling changes, or is this depending on your baud rate? So you basically go from like 20 megasamples to 10 and stuff like this.
Do you mean the adapter resampler?
Yes, exactly.
Here, right?
Yeah.
Okay, yeah, it depends, because if you see the end result at 25 kilobaud, my sensitivity level is actually 2 dBm off by what it should be. So I used to fix all of the sample rates to 1 mega, because 1 mega sample rate was working, no, 5 mega. I used to fix them to 5 mega, and it was working perfectly fine. However, yeah, you know, you see, there are some issues. There's actually, for the lowest baud rate, there's an issue here. Is that an answer? Okay, thanks.
Any other question, comments?
So on the SatNOX network, I see that there's quite a number of observations of your satellite at 70 centimeter wavelength. But is the S-band and your receiver, is that also available to SatNOX?
No. Because when you take photo of especially Turkey, just only Turkey, we have this directory of maps, and you cannot just publish that data. You need to get for a clearance. They say, okay, you can publish this picture. So it's not publicly available for now.
Okay, too bad. Thank you.
Just a general observation that in working in space and other places, I found that really, you need a reproducible build for your entire platform. And without that, you're doomed. If anything any place in your build system, it goes to the internet, you are losing. So, I mean, really, any of this, like use pip and go just pull down whatever, you're doomed. It will break. Anyway.
Thank you.
Great news.
Other questions, comments? No, then maybe we can get started with the next presentation. Thank you very much.
Thank you.
Good morning, everybody. Let me introduce myself briefly. My name is Gizem Özcan, and I am working as a telecommunications design engineer in Planes Satellite and Space Technologies. Our colleague, Dr. Meltem Köroğlu, is unable to attend this event. Therefore, I will present her work, and I will do my best. Thanks for your understanding in advance, and let's get started with the topic. Our topic is design and implementation of an adaptive data rate LoRa modem for LEO satellites using SDR and GNU Radio. Outline is, I will explain LEO satellites and IoT applications, and LoRa receiver and transmitter waveform structure, waveform properties, LoRa sensitivity values and data rates, and the adaptive data rate algorithm, and related link budget computation, and what is the channel model, LoRa pair performance and Doppler robustness, and LoRa waveform parameter estimation and our results. Then I'll show the GNU flow of this modem and results, then conclusion, and I will briefly explain our satellites and IoT products. LEO satellites are at orbit 160 and 20,000 kilometers, and as of 2024, there are approximately 5,000 and 6,000 actively LEO satellites in orbit, and LEO satellites enhance IoT applications because providing reliable and global coverage. And LEO's NTN means non-terrestrial network, and NTN IoT applications are increased because growing of the companies enter the NTN IoT system. And LEO satellites are used several purposes, such as communications, Earth observation, and IoT services. I will explain the long-range technology. Long-range, I will say LoRa, is a modulation technique, and its advantages are it has high Doppler frequency robustness, low data rates, low power consumption, long range, low cost, and multipath resistance. As you can see the figure, LoRa has more range and lower bandwidth, so low data rate according to other technologies. And these LEO's NTN IoT satellites are used for various aims, for example, agriculture, environmental aims, finance, insurance, maritime, energy aims. For example, reading the sensor data or reading the metering data, kind of. This graph shows the LoRa receiver and transmitter waveform structure. I will explain the blocks. At the transmitter side, input data undergoes the padding and CRC adding. It is preparing for the transmission. And then Hamming encoding is applied because error correction happens. And then whitening block, it is basically a randomizer. It randomizes the data. And then interleaving block, it is basically for spreads the data and prevents the burst of errors. And it is key parameters are SF means spreading factor and bandwidth. Then the interleaved data undergoes the graying block. It is mapping. It maps onto the interleaved signal to a specific modulation. In this time, our modulation is chirp spread spectrum modulation, and it is basically a LoRa modulation. And its important parameters are bandwidth, carrier frequency, and transmit power. And then this modulated signal undergoes a channel emulator. And channel emulator is used for simulating the real world conditions, like, for example, signal degradation, multipath effects, fading, interference, like that. And then after the incoming signal enters the receiver side, the incoming signal is first synchronized. The important parameters are spreading factor and carrier frequency because of the time and frame synchronization. And then signal is undergoes the demodulation and despreading block to recover the original data. And reverse of the transmit sides blocks, we have degraying, the interleaving, decoding for error correction, and then CRC check and padding removal is applied, and the original data is recovered as at the output. This shows the LoRa waveform parameters, and this is a graph, time and frequency. We use the preamble, radio sync symbols, header, and data and CRC. The preamble allows receiver to detect start of a new packet, and it consists up chirps. And then the radio sync symbols allows the receiver to synchronize the data, incoming data, and it has specific chirps. And then optional header come, and this contains the metadata about the packet. And data is the actual user data. As I said before, it can be sensor data or metering data. And optionally, CRC is added. Spreading factor is one of the important parameters for the LoRa. It shows how bits describes according to spreading factor increases, and it is range from 7 to 12. And our other parameter is bandwidth, and typically 3 bandwidth values used in LoRa modulation. They are 125, 250, and 500 kilohertz. Coding rate is related with the error correction capabilities, and it defines the actual data over actual data plus correction data. For example, 4 over 5 means 4 bits for data, 1 bit for correction. And for LoRa, the preamble length should be minimum 8. This spectrogram shows the comparison of LoRa spreading factors changing from 7 to 12 respectively. And you can see when the spreading factor changes, the slope and the time duration of the chirps are varying according to changing the SF. And you can see the formulations for symbol period is the chirp duration, coding rate, data rate, etc. And the packet structure is as follows, as I mentioned before. And the header explains, carries the metadata, for example, payload length, what is the coding rate, etc., like these kinds of information. LoRa sensitivity values and data rates. Sensitivity is the minimum signal level that can be detected by receiver. And our configurable parameters are spreading factor and bandwidth for this work. And if you see the table, we have spreading factor, bandwidth, sensitivity level, and data rate. So spreading factor changes from 7 to 12. And for the same bandwidth value, for example, 125 kilohertz in this case, the sensitivity levels improving, but the data rate decreasing. So higher SF values spread signal over time, increasing the chirp duration. This improves sensitivity, but lowering data rate. And to see the bandwidth effect, let's constant spreading factor, for example, 7. As the bandwidth increases, sensitivity level decreases and the data rate increases. So higher bandwidth allows high data rate, but requires more power in this case. So there are trade-offs, of course. This is our LoRa adaptive data rate algorithm. It starts with the received power computation at the module site. And link margin is computed as sensitivity minus received power. Then, based on calculated link margin, select spreading factor and bandwidth values, maximize the data rate while ensuring they have positive link margin. And then, using the selected SF and bandwidth values, the modulation is applied to the data for transmission. And again, the channel modeling. Then at the receiver side, the LoRa bank filter is applied to the received signal to unfilter the unwanted frequency components. And besides, the key point is to assist in estimation of SF and bandwidth values from the received signal. Then finally, the system demodulates the received signal using the estimated SF and bandwidth values, extracting the original transmitting data. Related link budget parameters are as follows. We have satellite output power as 13 dBm. Satellite antenna gain has maximum 8 dBi at another angle, and loss, of course. And for the link, free space pet loss, I will explain next. And for the atmospheric and ionospheric losses, we use the I2U model. And module antenna gain has maximum 3 dBi at another angle, and it has loss, of course. The inputs are satellite TLE data. I'll explain later again what is TLE data. Simulation start time, beacon period, module coordinates, satellite and module antenna gain, CST output files. And as an output, we have 3 outputs: free space pet loss, received module power in dBm, and Doppler frequency shifts. And the developed GNU Radio block for this link budget computation, you can see the parameters and input data and output data are used, mentioned in the previous slide. So free space pet loss is expressed in the equation, it depends on the carrier frequency and the distance between satellite and module. And we have the received power. It is calculated as a transmit power and satellite antenna gain, module antenna gain, and subtracting all the loss sources. Then sensitivity is calculated as noise floor, noise figure, and minimum SNR value. TLE data is two-line element data, and it describes current orbital parameters of the satellite. And you can see the structure of the format. Using this TLE data, orbit propagation applies mathematical models to predict the satellite's future position for expressing the satellite passing. And we use the model given in the link. The channel model have a developed GNU Radio block as shown, and SNR is calculated as received power minus noise power. Noise power is minus 174 dBm per hertz and plus 10 log 10 bandwidth. And clock offset and frequency offset are calculated in the equations. So for the two figures, it is expressed that elevation increases means satellite approaches, and elevation decreases means satellite moves away. So it describes one satellite pass. For one satellite pass, we can see this satellite receive power and module receive power increases when satellite moves to us, approaches us, and then when it moves away, the satellite and receive module power decreases. And for the Doppler, it is getting zero when it is just overhead and then increased again. LoRa packet error rate performance and Doppler robustness. Here you can see three figures. They are SNR versus pair graphics and for three different Doppler rates. And here we can see there is a 10% pair rate. And using the chirp speed spectrum, LoRa, data is encoded by the varying the frequency, the chirps over time, the duration and the slope, you remember. And this enables tolerancy for frequency variations and tolerant to Doppler effects. And for the bandwidth, wide bandwidth, when higher the bandwidth, relative frequency shift comes smaller compared to the narrowband systems. So this reduces the impact of Doppler shifts. And we see the low SNR performance in high SF values. This is our parameter estimation algorithm. First, the construction of all signal possibilities means from SF7 to 12 and for the three bandwidth values, construction of all signal possibilities, and then noisy signal, noisy received signal correlated, and for this block, selecting bandwidth and SF values have the highest correlation. So the output is estimated bandwidth and estimated spreading factor. Advantage of this robust estimation in power, in low power, noisy receiver conditions. You can see the estimation results here. First graph shows the spreading factor and correlation peak values for the three different bandwidth values. And for the optimal correlation is the highest one, as I said. So the second graph showed the estimated values. Spreading factor is 12, and the optimal bandwidth is 125 kilohertz in this case. This flow shows the adaptive LoRa modem GNU Radio flow. As I explained the block diagram, applying all blocks step by step, And you can see the link budget computation block, and it has, again, 3 outputs. And then the modulated data undergoes the channel modeling block. And the received signal undergoes the LoRa bank filter to estimation of the spreading factor and bandwidth values. Then the classical receiving blocks are applied, and then the signal is recovered. Test results are as follows. These graphics are against elevation angle, again, one satellite pass. You see in the first graph the received power. As we expected, the received power increases when satellite approaches and decreases when satellite moves away. And for the spreading factor, the highest spreading factor, 12, is applied for the weak channel conditions, for the worst conditions. And then between the 60 and 80 degrees, as you can see, the spreading factor is low. And for the bandwidth graph, the red one, it is optimally at the 125 kilohertz. And for the data rate versus elevation graph, it is the key point, because one satellite pass, as you can see, we increases the data rate. It is not constant. So when the satellite approaches, the data rate increased multiplied by 8, we can see. And there is a reduction in the 90-degree elevation. It indicates a balance between reliability and maximum throughput. And our conclusions are, we see LoRa packet error rate performance computed according to different satellite scenarios. That includes Doppler shift, free space loss, and noisy environment using GNU Radio and SDR. And LoRa Doppler robustness is observed according to simulated data paths suitable with the link budget. And adaptive data mechanism is developed by LoRa bank filter block, and higher data rates can be achieved during one satellite pass. As the elevation increases, the LoRa system optimizes its parameters, such as decreasing the spreading factor and increasing data rate to take advantage of the better signal conditions. The dynamic adjustment of a bandwidth at certain elevations enhances communication efficiency. And lastly, the system is designed to maximize data throughput and maintain link quality as the satellite or transmitter's elevation relative to receiver changes. And here are our references. And many of you were very interested in our company. Thanks for this. So I'll explain our satellites and IoT modules briefly. This is our first satellite, Connecta T11. It is a test satellite, and its importance is we learned how to make a satellite. The key points of this satellite, the design, development, and verification process were completed less than 1 year. And this is IoT-based communication satellites, so the experiments were conducted firstly for using this satellite. And the satellite has some procurement equipments, most of procurement equipments, but besides have subsystems developed within the planets. So we gained satellite heritage, our products, with this satellite. This is Connecta T12. This is the second satellite. These are 3U CubeSat structure. And importance of this satellite, it has optimized IoT payload and other subsystems with updates over T11. It is called a software-based satellite, and it is sent for the development and testing of Planes IoT technology. And this is connected to T21. It has 6U CubeSat structure, and it is a test satellite equipped with a high-resolution multispectral camera, and it is our first Earth observation satellite. These are the twins, connected T31 and T32. With these satellites, the inter-satellite link is verified between two satellites, and this is the first time to verifying the inter-satellite link in Turkey. These are our Connecta IoT 1, 2, 3, 4. It is a network. They are our beginning of the Connecta IoT network, and they are launched 2 weeks ago. And these are our first commercial IoT satellite batch for Planes. We are planning to progress as batches, and one batch includes 4 satellites. These are IoT products. For example, we have IoT module. IoT device manufacturers can integrate this model into their devices to enable direct satellite access with using the module. And IoT modem. IoT system integrators can connect their existing devices to satellites using this modem. And satellite access terminal. IoT solution providers can connect their existing IoT devices to connect to IoT network using this satellite access terminal. And I think there is a mistake loading this one link. No, I didn't see. It is wrong one. But I can find here.
Am I dreaming?
I want to show you a video. It is less than 1 minute.
How does the Connecta IoT network work? IoT sensor data is transmitted via Plan S modems, modules, or satellite access terminals. To Connecta IoT satellites operate in low Earth orbit. Ground stations are located in Turkey and various parts of the world. Data collected by Connecta IoT satellites are downloaded. Data from ground stations are sent to the Plan S core network. The data transmitted to the Plan S core network is parsed. The parsed data is delivered to customers through various platforms. Some of the sectors that benefit from the solutions provided by the Connecta IoT network are: all this communication is supported by a robust network.
Thanks for your attention. That's all for my presentation. If you have any questions...
Direct satellite communication service. Connecta IoT.
If you have any questions, you can directly email to Meltem Köroğlu, and of course you can ask me now. Thank you.
Thank you for presentation. Any questions or comments from the audience?
What is your threshold when you reduce your data rate again? Because it seems like you have very tight link margins, and you, like judging from the graph, I think you're already you're ready to accept high bit error rates also.
It is
like
about...
At which point do you switch down one?
It is about this?
Previously you also said that there's some logic to switch down.
For the link budgets,
here,
you say?
link margin computation. What link margin do you want?
Oh, where is the link? Yes, here. What's your question?
What link margin do you require, and what's your threshold below which link margin you switch down a mode? So, do you have acceptable?
Yes, actually, I'm not sure. I don't want to give a wrong answer. So maybe we can ask Meltem Köroğlu. It's conceptual.
Okay, so, our colleague actually did all of the theoretical work, so she knows the answer probably. And if you can write an email to her, she would be glad to answer that. However, she wasn't able to come and deliver the speech because she's actually right now testing it with IoT satellite. And don't go hard on Gizem,
2 weeks ago.
Thanks.
Yes.
Thank you. Other comments?
So just a small question about the hardware. So as I know, there are small modules available which contain a microcontroller and already a LoRa modem, a modulator, demodulator for something like 20 euros. So maybe with something like 40 euro one can already make some complete transmission, and the functions inside are already tested. So do you use this kind of available chips, or do you have to build your own hardware there?
We don't use that, you said. Yes. Don't use.
If I got the question correctly, you're wondering if we are using any COTS equipment in order to communicate with our satellite in the ground? Yeah, okay. Yes, exactly. That's why we have compatibility with them. So you can use it theoretically, but we do provide like mass solution for companies and so on, so standardized solution. You can of course use them with the satellite.
Yeah, there are only so many parameters for preambles of a LoRa package. Do you ever get problems with, like, there are vast IoT networks based on similar chips that the modem is just overwhelmed with other similar systems sending stuff that just happens to reach also space?
She can ask. She knows the work.
Well, we have just launched the satellite 2 weeks ago, and we are in the middle of commissioning. So we've started to see some problems, but it's not certain yet. And well, actually, this week we were here, and team was in Turkey. So as far as I've caught up with them, there seems to be no major problems at all. But we are still testing. We're at the very beginning of this in terms of testing in space with real-time applications. However, we observed that it was able to get some signals even though the antenna was not deployed. Yeah. Yeah. Well, this may be a software bug too, or I don't know. Well, we are checking it.
So I guess you're using commercial modems for LoRa, so Semtech or something like that, no?
Yes, we use.
Okay, so my question would be, so it was my fault. Let me, okay. So please tell us what technology you're using for the modems. That would be interesting. And then forward-looking question, would you be interested, or would anybody be interested in implementing LoRa as an SDR? Because that would be quite more interesting, I think, so than just using proprietary chip. That was my question.
Okay. We do not use modems as in the sense as a like complete solution, but we do use some, you know, universal chips, of course, and universal waveforms as well. And yes, I think we all would be interested in developing a GNU radio-based LoRa modem.
Hervé, any comment about LoRa modem using SDR?
You want to tell me yeah, okay, about GNU Radio implementations of LoRa. There are two implementations. In fact, the original one that's a bit out of date, and a new one from Switzerland. It's quite recent, and well, it's really interesting if you want to go into the details of LoRa communication.
And I mean, not to make too much of an advertisement for GRCon out of this, there's actually 2 talks on LoRa GNU Radio implementations, so you might want to watch the streams. So yes, this actually works, and you can do it. And I think what Andreas was pointing out is that you can't, like, there's very many LoRa devices with a commercial off-the-shelf chip that's not, what's it called in LoRa, a concentrator. You can only do more or less one communication partner, which probably won't be very helpful for a satellite network.
I have a question. As far as I know, LoRa is a proprietary standard from Semtech that has been pretty well reverse engineered. So I don't know what the licensing is of this standard, or if you can just use it. Because to my knowledge, people just had this modem which was pretty easy reverse engineerable.
May I give a lawyer's? It depends. Yes, there are like open solutions. So it's published in IEEE standard, so it's an open standard. But the theory is open, but the specific implementation algorithm is patented. So if you want to use it for commercial purposes, you need a license, which I think they say is more or less lowish, free-ish, but it's not free, libre, open source software. So there are some conditions. Maybe you're at the source, you know more.
I don't know anything about it.
Because I looked at it for private reason, I was curious, and I thought, like, oh, let's implement it, put it out in the world, and yeah, lawyers.